bootstrapping, things like that, to massively increase the noise robustness. So short answer is, and those are all built into PySyndy, that open source package. So again, that's a problem that's becoming increasingly solved as time goes on, but it is a real problem.
Great, thanks so much. Unfortunately, that's time, and there's a lot more questions in the Q&A and the chat. So
awesome. Well, thank you so much.
Yeah, I apologize. I couldn't get to all of them, but thank you so much for joining us and for the wonderful talk. And yeah, let's thank our speaker one more time. All right, Rose, I guess you're next. Hi, welcome.
Hi.
Thank you for joining us. Are you able to share your screen? Does it work?
Yes, I think so. 1 second. Can you see the slide?
Yes, I can see. So great. So thank you. So I guess I can introduce you. So our next speaker is Dr. Rose Yu, who is a assistant professor at UCSD in computer science and Gal is going to kill me. I can never pronounce this right. The Holgu data science.
Oh, Halikuju. Yeah, it's very difficult. It's a Turkish name.
Dr. Yu is here to tell us about her work. She's been doing some fantastic work in both physics-inspired ML, and as well as I've been fortunate to start seeing, digging into her work on tensor models and their connections to dynamical data and to other models like GP. So we're very happy to have you. Thank you for joining us, and it's all yours.
Thanks, Adam. Thank you for the invitation to this wonderful workshop and the winter school. So today I've decided to talk about something different than physics-guided deep learning or tensor methods, as Adam mentioned. I'm going to talk about some new work from our group on uncertainty quantification. So I direct Spatiotemporal Machine Learning Lab, and the mission of our lab is to advance machine learning for large-scale spatial temporal data. And this is a logo of our lab. And as you can see here, there is a picture of Rose, which is obvious, but what's not obvious is there's also a letter S and T stands for spatial temporal. So that's the name of our lab. So I will motivate the problem of spatial temporal learning using the example of pandemic modeling. So we know that pandemic is only increasing in frequency, magnitude, and complexity. And it's really making creating a lot of difficulties for our life. So if we can, making forecast of deaths in a hospitalization is important for informing public health decisions. So in epidemic modeling, the traditional models are mostly based on mechanistic physics-based models. And one, they are very expensive to simulate at high resolution. Two, they sometimes rely on very rigid assumptions of underlying dynamics and full observability. So the effort that we've been doing in the past 1 year or so, actually about 2 years, is to introduce data-driven methods and combine that with mechanistic models in epidemic modeling to hopefully relax these assumptions in modeling dynamics and speed up the simulation for rapid scenario creation. I will begin by talking about this work of deep uncertainty quantification. Obviously, when we think about machine learning, deep learning is perhaps one of the hottest topics nowadays in making predictions of all kinds of applications. It has achieved huge success in computer vision, natural language processing, and also in dynamical systems. However, a lot of the deep learning models, they are deterministic, so they can only produce point estimates they cannot quantify the uncertainty of the prediction, which is actually critical in the application of epidemic modeling, because we wanted to be able to generate predictions with confidence intervals, which help us to assess risks of the prediction and help us make better decisions. I will begin by discussing our recent effort in forecasting COVID-19 mortality rates. So this is a screenshot from the CDC website today. And this shows the new weekly deaths over different weeks. And this is generating 4 weeks ahead forecast using a combined forecast. So this is a combined forecast about 30-ish models. And our model is one of them. And this is a ranking of the model in terms of uncertainty quantification. And you can see that among all the 30 teams, our model, the UCSD NU DeepGLEAM model, which I will talk about next, achieves the highest performance, the best performance in terms of uncertainty quantification. So this is a joint work with my PhD students, Alan, and our collaborators, EMA at Hardy-Cuju Data Science Institute, and our collaborators from Northeastern who are experts in computational epidemiology. So first, we need to talk about what type of deep learning models are good for spatial temporal forecasting. So formally speaking, if we want to do forecasting for a multivariate spatial temporal time series, we can characterize the system by a variable state, and we call it xt. So xt is the state of the system at time t. So in the application of COVID-19 modeling, it can represent a vector that consists of number of cases at different locations. So it's a multivariate state. Then the goal of forecasting is to learn a model F that maps from the sequence of previous state x0 to xt into a sequence of future states xt plus 1 to xt plus h, where h here is the forecasting horizon. So what's unique about spatial temporal forecasting is that when we do forecasting in order to approximate underlying system dynamics, is that we need to capture both the spatial and the temporal dependency. When we make predictions of mortality of different states, it's obvious that these states are correlated with each other through travel. And then on the right-hand side, you can see the dynamics of the system is highly nonlinear. So the number of cases cannot be simply captured by a linear model. So how can we capture this type of spatial temporal dependencies with deep neural networks? In terms of temporal dependency, actually it's very similar to the sequential dependency in large language models, because we can think of the sequence of time series as sequence of tokens. And in this case, we can just use any sequence models that are very popular, for instance, a recurrent neural network. So it has this encoder-decoder architecture where the encoder will encode the past information from x0 to xt into some hidden states, and the decoder will generate the future forecast of xt plus 1 into xt plus h, given the encoded hidden states. So mathematically, given the input state xt, an RNN will map that into some hidden state ht, and this ht, the hidden states, is being updated recurrently, hence the name recurrent neural network, and then the output is another nonlinear function of the hidden states. So in our case, the output yt is the state at the next timestamp, xt plus 1. So that's not new in terms of temporal dependency modeling. But what's different here is how can we model the spatial dependency in multivariate time series? We know in image data, when we model the spatial dependency among pixels, we can think them as values distributed on regular grid. So we can instantiate convolutional neural networks, which intrinsically have translation symmetry to model this type of spatial dependency. So when we think about the spatial dependency in the epidemic setting, we make the analogy that the disease spreading is similar to the diffusion process on a directed graph. So we proposed this type of new convolutional operator that can operate on this irregular grid. So that leads to the diffusion convolutional network. In this case, the nodes corresponding to different locations and the edges represent the proximity between locations. So in epidemic modeling, the proximity can be calculated explicitly using air travel data. So diffusion convolution is defined as follows. This actually comes from our earlier paper for modeling traffic flow. And we actually extended this model slightly to model the diffusion process of the epidemic. So given adjacency matrix Aij, which is the representation of a graph, each element in this adjacency matrix is defined as some distance between the two nodes Vi and Vj. As I mentioned, this distance can be calculated using air travel. Given the adjacency matrix, we can define the in-degree and out-degree matrix, which is the row sum and column sum of the adjacency matrix. So there's this really cool theoretical results from graph theory, which characterize the stationary distribution of a diffusion process. It states that the stationary distribution of a diffusion process can be represented as a weighted infinite random walks on a graph. So this matrix, the D inverse O times A, is called the random walk matrix in graph theory. And when we raise this random walk matrix to different powers, it represents the random walk over different number of steps. So we have a coefficient theta of k, which characterizes the speed of diffusion. So this stationary distribution P essentially can be written as an infinite sum of random walks. So in the classic setting, this type of parameter theta need to be calculated. But our idea of diffusion convolution is to make these parameters theta trainable in neural network setting. So this is the formula for diffusion convolution, essentially given the state of the system, xt. So this represents the concatenation of number of cases of all the locations. In our case, it's different states or different counties. And this diffusion convolution will essentially transform the input state using the graph information. So it applies the graph random walk matrix to different powers, and then we characterize the diffusion process with a bidirectional diffusion. So the first term represents out diffusion, and then the second term represents the in-degree diffusion. So when we combine these two systems together, it models the diffusion process on the travel network. And then the weights here can be learned through backpropagation, and xt is the input to the system at time step t. Pictorially, diffusion convolution characterizes this type of dynamics where imagine we have certain groups of people who are actually highly infectious, then they will travel to different locations, which will affect other people. So it can be visualized as this type of random walk into the first order neighbors, the second order neighbors, and etc. So these coefficients in front of the diffusion represent the diffusion speed and the weights of each step diffusion. And these are trained using backpropagation. So essentially what we need to do here is to incorporate this diffusion convolutional operator into any sequence architecture. So remember, we have a recurrent neural network that models the temporal dependency. And then this operation between the weight matrix W and the input state xt is a matrix multiplication. So for a vanilla recurrent neural network, it does not model the dependencies in the state xt. However, if we wanted to introduce spatial dependency, what we can do is to simply replace the matrix multiplication with our defined graph convolution. So in this way, we can capture the spatial dependency within a sequence model. Okay, so this so far is only about a deep neural network that can make spatial temporal forecast deterministically. Because as you can see here, the equations have no stochasticity in, by definition. So how can we make a deterministic model generate probabilistic forecasts? So we had to look into the literature of uncertainty quantification in deep learning. Essentially, we summarize different uncertainty quantification techniques in a unified framework. So specifically, given some data X and then the output, some response Y, we have parameters of the distribution that we want to capture. We can write out the prediction problem as a regression between the ground truth predictions, the response, and the prediction from our neural network model. So the expectation is taking over subsamples of data. So this type of F, the function, is approximated by a deep neural network, and in our case, is approximated by the diffusion convolution of recurrent neural network to generate sequence of forecasts. Usually, uncertainty quantification can be characterized into two groups. In the Frequentist UQ method, what we do usually is that given the particular parameters of the distribution or the neural network, we will take expectation of the errors between the prediction and the ground truth for that particular data, and then we will take the average over the parameters of the distribution. So essentially, Frequentist UQ captures the variations in the data. On the other hand, Bayesian uncertainty quantification swap the order of which we take in expectations over the data or over the parameters of the distribution. So given the particular instantiation of the data, Bayesian UQ will first calculate the deviation with respect to the particular data set, and then taking average with different instantiations of the data. So essentially, Bayesian UQ will capture the variations in terms of parameters. So within Frequentist UQ, which captures the variations in data, there are a lot of different methods. So in this paper, we conducted a systematic benchmark study of all these different UQ methods and also proposed our new variations of UQ for deep spatial temporal forecasting. In Frequentist method, the classic one is quantile regression. So this essentially boils down changing the loss function of a forecasting problem into this type of loss as the pinball loss. Given the prediction y hat and the ground truth y, quantile regression will calculate the loss by looking at the deviation from the ground truth with this confidence interval tau. So for a given particular confidence interval tau, it will reweight the gap between the error according to tau. So if it's larger than the ground truth, then it will reweight the error by tau. And if it's smaller than the ground truth, you will reweight the loss by tau minus 1. So that's the essence of quantile regression. So for different quantile confidence interval, we need to train different deep learning models in order to generate the interval of the forecast. An extension of quantile regression is called mean interval score, or MIS, which comes from statistical literature. So essentially, it generates not only the difference between of the particular confidence interval, but it also penalizes the size of the interval. So MIS regression will ask the neural network to generate three things: the prediction y hat, the upper bound u, and the lower bound of the prediction. So a deep neural network will have to be modified to generate to have a multi-head output that generates these three things simultaneously. So an MIS regression can be formulated as a loss function in the deep neural network, and then we can penalize the error term and the size of the interval, which is defined as a difference between the upper bound and lower bound, as well as how much the prediction is exceeding the upper bound or the lower bound. And obviously, a classic Frequentist UQ method is called bootstrap, and then that's basically training the neural network with different resample data without replacements. So in Bayesian UQ, which captures the variations in parameters, there's also several classic techniques. One of them is developed by our collaborator EM called stochastic gradient MCMC. So in training neural network, the common method is based on stochastic gradient descent, which means we will update the parameters of a deep neural network data using a mini batch of data, and using that mini batch of data to calculate the stochastic gradient. So eta is the learning rate, and then theta k represent the parameter update at case iteration, and del of L tilde represent the stochastic gradient. Here, the only thing we need to modify for stochastic gradient in order to obtain uncertainty quantification with SGMCMC is to add this type of noise, P of K. So we can prove actually if this P of K, the noise satisfies certain distribution, then the posterior actually will converge to the true posterior of the Bayesian distribution. Therefore, it gives the uncertainty of the parameters. So this picture shows sort of the dynamics of stochastic MCMC and how it actually converges to the stationary point. So this is one type of Bayesian UQ method. The other type of Bayesian UQ method is probably very well known, called Monte Carlo dropout, proposed by Agel and Gaharmani many years ago. So the idea is that we can randomly set some weights in the neural network to 0, and it provides a very simple alternative to variational Bayes. It gives the uncertainty of the prediction in the Bayesian sense. So remember, we have a deep neural network, which is deterministic. So what we did is to benchmark all these different UQ techniques and then see which one performs well for our particular application of forecasting. But to our surprise, if we just use deep neural network to predict the raw numbers of mortality, the performance was terrible because the data was very sparse. The data we collected actually come from Johns Hopkins. And the data set we use is the number of cases reported every week. And the data is extremely sparse and has a lot of missing values. So using a deep neural network to directly train on data give us very poor performance. So instead, what we did is we combined the predictions of deep neural networks with the prediction of a mechanistic physics-based model called GLEAM. So GLEAM is a physics-based model that simulates the progression of disease by integrating different type of information, such as airport, commuting network, and population. So as I mentioned, GLEAM model itself assumes full observability. So it doesn't capture this partial observability and stochasticity all known in the dynamics. So our model, DeepGLEAM, is a very simple idea where instead of modeling the dynamics of raw counts of mortality, we're modeling the dynamics of the residual between the physics-based model and the observations. So this function f, which is now a neural network, is approximating the residual between the ground truth, the GLEAM model, which is a physics-based model, and the prediction R, which now is modeled by a deep neural network, and F represent the ground truth dynamics. So essentially, we take the predictions from the physics-based model, subtract that from the observations collected by Johns Hopkins physics lab, and then we use that data as an input to our neural network. So this neural network is a diffusion convolutional neural network. As I mentioned before, it takes the input state xt, right, representing the number of counts for different states. And then it takes the graph information, which is a travel graph across different states. And then it generates the embedding into the hidden states. And then it has the encoder architecture and then pass on to the decoder to generate future forecast. So in this case, we're generating 4 weeks ahead forecast for mortality. Okay, we also did this benchmark study for different methods, right? As I mentioned, we can modify this base model with different techniques such as quantile regression, MIS or mean interval score regression, and Monte Carlo dropout. So this shows the forecasting into 4 weeks ahead forecasting, week 1 to week 4, of different metrics. MAE is the mean absolute error, which quantifies the quality of point estimates. And then MIS is a mean interval score that gives the score for both the point estimate performance as well as the coverage. Interval width is just the coverage alone without the point estimate error. So we can see in general, the conclusion seems to be that the Bayesian methods such as SGMCMC, right, which has a capital B here, represent Bayesian method, and MC dropout, these two methods gives very good point estimates. So the bolded form numbers are the best performing ones. We can see that for MAE, right, the Bayesian methods are generally outperform the other methods. So it gives very accurate point estimate forecast. Because our data is very small, so we hypothesize, using Bayesian UQ has certain advantage over sparse data, which is not surprising. And then when we look at the coverage on uncertainty quantification, actually simple, the frequentist methods such as spline quantile, the variation of quantile regression, MIS, which directly optimize over the MIS, not surprisingly achieve the best performance in terms of coverage. So we can also look at the actual forecast from our model. So this shows the weekly death over the US and different states. The black solid line is the ground truth, and the green shade shadow represent the quantile regression, which is an instance of Frequentist UQ method. And then the orange line is the SGMCMC, which is an instance of Bayesian UQ method. So we can see that, so this, after this dashed line represent the forecast, because in generally, the confidence interval generated by Bayesian method is much narrower than frequentist methods, quantile. So that explains why quantile regression achieves better MIS scores or better coverage. But in terms of mean prediction, the point estimate prediction, SGMCMC follows the variations in the data quite closely, as opposed to quantile sometimes smooths out the forecast. So it partially explains why SGMC or Bayesian method gives better point estimates. And we also did a lot of different studies in this paper of other applications beyond COVID-19 forecasting, such as traffic forecasting, air quality forecasting, and the observations seem to be quite consistent for the comparison between UQ and the comparison between Bayesian UQ and Frequentist UQ. Okay, so this is about forecasts, right? But in COVID-19 modeling, forecast perhaps is not the most urgent task. Another important task in COVID-19 modeling is scenario creation. So this plot shows a toy example of scenario creation. So if we have the number of cases forecast for a particular variant of COVID-19 virus, and then now we have Omicron, right? What if we have a new variant? So the characteristics of virus will change. Then naturally we would ask the question of what if. So what if we have a different virus? What if we have a different policy, right? What if we have a different masking or vaccination strategies? So this is a problem of scenario creation. So what we want is to have rapid scenario creation, right? And obviously in epidemic modeling, the traditional methods are largely based on stochastic simulations. So these are stochastic differential equations being simulated at a very high spatial temporal resolution to account for different kind of travel patterns, characteristics of virus or policy changes. So we can expect that because the simulation is stochastic, so for every scenario, which means a particular set of parameters of virus characteristics, policy changes, we need to simulate thousands of possible trajectories and then take the aggregation of that simulation to represent a potential hypothetical scenario that would happen. So because of that, stochastic simulations these days are very expensive computationally. So it typically takes a couple weeks to simulate for a different scenario. So that's not sustainable. And the goal of this project as a follow-up of our previous work is to learn a deep surrogate model that can rapidly generate scenarios and speed up complex simulations. So this is a work led by my PhD student, Alan, and again with our collaborators at UCSD and Northeastern. So in surrogate modeling, there are actually a lot of experts here. The Paris have done wonderful work on surrogate modeling. Actually, Gaussian process is perhaps the most common choices for surrogate modeling, right? Because we can place a prior distribution on this function f of x. So this shows a very simple example of Gaussian process. Let's say the function f is a sine function where fx equals x times sine of x. We can place a prior on this function, which is now represented by a Gaussian process. A Gaussian process is characterized by a mean vector M and the kernel matrix K. So the kernel will characterize the similarity between the adjacent 2 points. And then when we plot out this Gaussian process distribution on this assigned function, it will give us the uncertainty that we want. But we know that, in this full-fledged Gaussian process is quite expensive because we need to calculate the inverse of the kernel matrix. There are a lot of development in scalable Gaussian process, but the alternative that we take is to combine neural networks with Gaussian process, and that leads to this line of work, which has been studied recently actively in machine learning community called neural process. So this work of neural process originally was proposed by Garnello a couple years back, where the idea is to provide a much more flexible and scalable alternative to Gaussian process, where offer the same functionality of characterizing uncertainty and become surrogate models. So in Gaussian process, we have explicit kernels, but in neural process, the idea is we can replace the kernels with data-driven priors. So in this case, this is a picture of a neural process where we have some input data, X and Y pairs, where X is the input, Y is the output. And then we can encode this input data into the data-driven priors Z as a latent variable. And this latent variable will serve the purpose as kernel functions in Gaussian process. So then given these kernels, then we can generate forecasts for a new set of pairs. So given new set of input xt, it will generate the new set of outputs yt. And then the inference procedure is shown in this right plot. It's a little bit complicated that I will not explain in detail, but the idea, it follows a type of variational Bayes paradigm, where we have some input data and we encode that into latent variables, and these latent variable represent the kernel function that are inferred from data. And then during the inference phase, we can generate predictions given these latent variables. So because of the latent variable modeling, so we can follow the typical variational inference technique to optimize the lower bound of the log likelihood. So this is actually the lower bound, or also known as evidence lower bound, the elbow function of the log likelihood. So instead of optimizing the left-hand side, we're optimizing the right-hand side of the equation, and that gives us a lower bound of likelihood. But once it's trained, it can give us a way to perform the inference, which is to infer the kernel function given input and output pairs, and then give us a way to do generation, which is given some input, how can we make predictions of our output, right? In our case of scenario creation, the input is the initial condition, the parameters of the dynamics, and the output is the state of the system, represent the future forecast of number of cases into 4 weeks. So neural process itself doesn't capture spatial temporal dependency. And our contribution here is to extend neural process to spatial temporal setting. As I mentioned, we have various ways to capture spatial temporal dependency, in particular using diffusion convolution or recurrent neural network. So the modification we did on top of neural process is, one, to introduce this latent process, which allows the kernel to vary over time, and two, to use diffusion convolution to capture the spatial dependency. So in this application, the state of the system, xt, represents the daily prevalence and the incidence of each compartment, such as infectious, susceptible, etc. And then it also, that's the output of the neural process, and the parameters data represent the characteristics of the virus, such as reproduction number, the contact rates, etc. And these are the input of the model. So we introduced latent process to represent this unknown dynamics over time, and then we use diffusion convolution to capture the spatial dependency, as explained before. So this is our model, which we ended up with spatial temporal neural process. Essentially, it takes the county level parameters data and generates some latent parameters. You can ignore the intermediate mechanism, but it's you can think about it as a functional approximator that approximates a map from parameter space to the latent process. And then the decoder, on the other hand, will map the latent process into the actual state of the system, the sequence of state representing the number of cases over the next few weeks. So this neural process essentially gives the surrogate model of the underlying dynamics while capturing uncertainty. But in order to train this model, we have to generate a lot of simulations from our physics-based model in order to have a good prediction. But as I mentioned before, simulating different scenarios itself is very expensive. So we cannot really afford to generate a large number of simulation scenarios to train this model. So instead, we propose this type of active learning pipeline, where we can actively select the scenarios that we want to use as training data and iteratively train the model on the fly. So given the neural process model, we will learn the latent process. So now we will ask the neural process model to give us some predictions of the scenario where it's uncertain. So using some given different parameter setting, these are the input, we will ask the neural process model to make some predictions of all kinds of scenario. And then using these predictions, right, where right now in the first iteration, the neural process is actually very bad because it's trained with very few scenarios. So we ask the neural process to make a rough guess of the possible states of the system. And then we use an acquisition function to intelligently select the scenarios represented by different parameters that are most informative for training. And then we will go back to the simulator to ask the simulator to give us more training data. And then we will augment the training set with a new set of simulations and then retrain the neural process iteratively. So this way we can avoid the case where we have to generate massive number of simulations. And two, we can understand where the model is most uncertain and then only select these scenarios to train the model. So instead of learning passively, we're querying the simulator actively. So the neural process model as a surrogate model is interacting with the simulator in real time. And then the high-level idea of how we can select this scenario is based on the information gain. In active learning literature, there's actually a lot of different acquisition functions that people have proposed to actively select the scenarios as training data. For instance, Gahamani proposed to use the maximum standard deviation. So by measuring the standard deviation, we can approximately know the uncertainty of the prediction and using that as a criteria to select the training data. And obviously there's maximum entropy, which give us the chaos in the system, and we will select the scenario with maximum entropy. And there's also a Bayesian active learning divergence, or BALD, is also used in the deep learning sense for active learning. So you will calculate the information gain between two distributions. So this is the information gain, right? Calculate the difference between two entropies. So with and without the latent process, how much information we're gaining. Unfortunately, in our particular model, the second term is intractable because we don't have the full-fledged posterior distribution. So instead, in this paper, we propose an alternative to information gain called the expected latent information gain in the latent space, because we can generate the latent process. And this new information-based criteria, LIG, the latent information gain, can be calculated using the KL divergence between the posterior of the latent information and the prior distribution and latent process. So we provide theoretical guarantees of the behavior of latent information gain. Essentially, under the assumption of random feature map, we can show that using latent information gain as an acquisition function, it will lead to an order of sigma d divided by root square t sample complexity. So which means the model will be able to reach a particular error in terms of latent process with order of the d is the dimension of the parameter, t is the number of timestamp. Whereas if we do random sampling, then it will be order of sigma the standard deviation of noise, and d squared divided by square root of t. So we can see that just by simply changing the acquisition criteria from random sampling to greedily select based on latent information gain, we can obtain order of d reduction in sample complexity. So that means if we have a higher number of dimensions in a parameter space, then using latent information gain to perform active learning will give us better gains in in sample complexity. So this is kind of the whole pipeline of our deep Bayesian active learning framework for scenario creation. We have simulation data, and we have a trained neural process as a surrogate model. We learn the latent process using neural process model. We infer the approximate estimations of different parameter settings, and then we use acquisition function to select the scenarios, and then add that to the training set, query the simulator, go back to train again. So we can iterate this pipeline many, many times. And once the model is trained, it will become a surrogate model for the physics-based mechanistic simulator, but much faster, because the inference of neural process is very fast. It doesn't have to go through expensive numerical integration or Monte Carlo sampling. So just to test whether this pipeline works, we start with a toy example of SEIR. So an SEIR model is a discrete Markov chain. So it has 4 different compartments, and then from state S to state E is characterized by this transition parameter beta. And we have the total population of 100,000, and then these different individuals will go to different compartments with certain probability. So epsilon is the inverse of the latent period, so that it decides the probability of which an individual will enter the infectious state from an exposed state. So we will vary this parameter epsilon from some range, represent different scenarios, and then we will vary the transmission rate beta in a different range. So these two combined decide the scenario of the simple pandemic dynamics, and we can vary the parameters in this range to represent different scenarios. So given that we will simulate 100 days of epidemic and generate 300 scenarios, we have 30 samples per scenario. So this is a simple dynamics where the scenario is characterized by 2 parameters, epsilon and beta. So we can sort of look at the behavior of our acquisition function compared with different other alternatives. So essentially, this top plot, this is the 2D plot where the axis represents these 2 parameters, epsilon and beta. So each point in this grid represents a scenario. And then this blue grid represents the prediction error for that particular scenario. So this is a heat map, right? And then we start with same initial condition. We have two dots represent 2 scenarios that are already included in the training set. So we start training our model with 2 scenarios. And then in the iteration 1, we have the black grid represents the value of the acquisition function. So that gives us the reward of which selecting this particular scenario will give to the model. So after first iteration, we can see that the LIG will generate this type of acquisition function, which shows that this area will give a lot of information if we sample in this area. And the white one will show that if we sample from this area, it doesn't give us much information again. So we will guide the model to select these different places to add that to the training set. So we can see that compared to other baselines, such as mean standard deviation, maximum entropy, or random strategy, right? Using LIG really give us a good exploration and exploitation trade-off. So after only 2 iterations, the model has already learned a pretty good surrogate model. So the MAE is quite low, close to 0. And the samples actually are uniformly scattered in this area. Whereas if you use mean standard deviation or maximum entropy, you can see that the samples selected according to this criteria are clustered in this area. So there's overexploitation in these type of acquisition functions. So we can also compare the behavior of Gaussian process with neural process. As mentioned, the goal is to provide a much more scalable and flexible version as Gaussian process. But for the simple example, we want to make sure it actually indeed can learn similar behavior as neural process. So this is the infectious population over a number of days. And the truth is in blue, and the orange line is neural process, and the green line is Gaussian process. We can see that neural process actually fits better than Gaussian process for mean prediction. And then in terms of uncertainty quantification, Gaussian process gives a wider uncertainty in some confidence intervals, actually reflect the true uncertainty of the simulator. The right plot shows the prediction error versus percentage of data. So this to trying to compare different acquisition functions and their effect on these two different models. So we can see that with latent information gain, we might obtain a quite good accuracy with only 4% of the data. So that shows the advantage of using active learning. Then we applied this model to a large scale study of LEAM-US. It's a stochastic epidemic model. In this case, the number of dimensions in the parameter is actually close to 16,000. So this kind of size makes Gaussian process no longer feasible to do calculations anymore. So we apply our neural process model to this simulation. So we generate about 300 scenarios, and we have about total 16,000 sample sequences. So when we apply our neural process model, we can see that the model can mimic the behavior of the simulator quite accurately. So the blue line is the ground truth, where the prediction is the yellow line. So the yellow line closely follows the blue line for different compartments, such as symptomatic, asymptomatic, removed, etc., which shows that the model has indeed learned the correct behavior of the simulator. So when we also looked at the acquisition function behavior, so this shows the prediction error versus the percentage of data. Because we're using active learning, we can learn similar behavior as offline training, which is the dash black line. So this dash black line is to train the model with all the simulation data, where the other lines is using a partial of the simulation data using active learning. So we can see that the model achieves comparable performance by using only 30% of data. So that achieves 68% data reduction than the offline model. So to conclude, I talked about essential two effort that in our group trying to quantify the uncertainty in deep spatial temporal forecast, apply that to epidemic modeling. So in deep spatial temporal UQ, we conduct a systematic study of UQ for spatial temporal forecasting, where we observe Bayesian methods are typically more robust in mean prediction, whereas frequentist methods provide better coverage. And I talked about another work of interactive neural process, which is to use deep Bayesian active learning as a surrogate model for scenario creation. So we can see that neural process provide a flexible and scalable alternative as Gaussian process, and using information gain on the latent space significantly reduce the sample complexity of learning. So with that, I would like to just end my talk. You can find the code and the data on my website, or follow me on Twitter. And here is the funding agencies that support this work. Thank you.
Thank you, Rose. That was fantastic. I will start with the question in the chat. Let me pull that up. George asks, it seems that, or it says, fantastic talk, thank you. It seems that this approach assumes that the spatial and temporal dynamics are separable, one modeled by a latent space model and the other by graph diffusion. Would the same approach work for a spatiotemporal process that cannot be decoupled?
I don't think we assume the spatial temporal dependency are coupled, right? So if you like, let me show you. How can I? Let me go back to the equation that I described. So okay, so right, then in this equation, you can see that what we did is to replace the the operation of matrix multiplication with diffusion convolution. So the spatial dependency now will transform the state at time t. So hence you will also transform the hidden states in the temporal dynamics. So they're not separate because we're using the spatial information, right, to change the dynamics and assume that the dynamics of different time series are coupled. So we're not assuming spatial temporal decomposability in that way. And actually, what we implement in practice is we use a memory-based recurrent neural network, such as an LSTM or the gated recurrent unit. And what we did, we will actually change the memory, how the memory is being calculated using diffusion convolution. So the spatial dependencies will enter into the memory of the dynamics, so they're not separate.
Thank you. From the Q&A, Andrea asks, quantile regression doesn't give coverage guarantees for finite samples. Did you think about using methods that do, such as conformal prediction and specifically conformalized quantile regression?
Yeah, exactly. I mean, that's a wonderful question. So we actually we're writing a paper right now about that particular angle, right? So obviously the techniques that I talked about, such as quantile regression or MIS, they can be combined with conformal prediction, and to have finite sample guarantees in test time. But obviously the downside is in conformal prediction we need to split the training set into the actual training set and the calibration set. So for our application, because the sample size is already so small, we cannot really afford to split the data into two sets, and that actually degrade the performance, and what's what our finding in practice. But I think in general, I really like your suggestion of having finite sample guarantees for coverage and using conformal regression, or even there's a lot of follow-up work after conformal quantile regression.
Thank you. Another question from the Q&A. Excellent talk. Shin asks, are there any other uncertainty quantification metrics that is applicable to deep spatial temporal method? So I guess this is similar to the last question.
I guess yeah, I mean, because we talked about different techniques that we use, right, in spatial temporal forecast. I guess there are observations of Bayesian versus frequentist in this particular context. So I guess I'd be happy to know more if you have good suggestions of UQ method.
Thank you. I had a quick, just a curiosity that I know something, in the last plot you showed where you were assessing the percent accuracy versus using all of the data. I don't know if it's easy to pull that slide back up.
Oh, yeah, let me do that right now. This is the slide that you're talking about?
Yeah, yes, thank you.
Mm-hmm.
Is it, maybe I'm not understanding the relationship between the data being sampled online and the, kind of the ground truth black line offline version, but it looks like LIG is starting to dip below rather than converging to. Is that something with just how the data is being sampled separately?
So it's actually, I think that, it's slightly below. It's just perhaps due to the variations in training and sampling. Okay. Because what happened is that in this particular setting, right, we first generate a large number of simulation up front, and then we train our offline model using all the data. And then we given the data pool, right, we use active learning to select a simulation from that data pool. So and so here, the comparison for LIG is done in that way. And we know it sometimes it may, just like, even using the exact same set of data as training, because of variations in, stochastic gradient descent, and also the sampling of the, the order of which we sample the data, it will create variations in performance, slight variations.
Excellent, thank you. Okay, great. So thank you for clarifying that for me.
Of course.
We have another talk from the Q&A, an anonymous, a really amazing talk. Can we model predictive control techniques using the spatiotemporal autoencoder architecture you described for pandemic modeling? How well can this type of method handle noise in the input data?
Right. I mean, that's a really great question. I think, I would say generally the answer will be yes, right? Because when you do MPC, like you wanted to generate predictions with uncertainty, and you can use that kind of uncertainty to guide the controller. So in our case, we can use this model, right, to generate hypothetical scenarios and with uncertainty, and you can feed that uncertainty into, in our case, is the controller is actually just the simulator itself, but you can replace that simulator with the actual controller, right? So I guess the other question is that how does it handle noise and emissiness? In this case, right, the second example I talked about, the data is actually not noisy because they're from the simulator. But the first work I talked about, which we combine physics-based prediction with deep learning prediction, is really able to handle the scarce data or missiness in the data, because the COVID-19 records are extremely noisy. So that's I don't know whether that answers your question. Yeah, but I would love to see whether this type of tools can be used in MTC, and what are the challenges there.
Thank you.
Mm-hmm.
Do any of our panelists have any other questions? All right, so I have an extremely basic question, just because I'm new to the uncertainty quantification for neural networks. One of the first things I read about was Bayesian neural nets, and I'm wondering how they relate to some of the ways that you've described here. I'm wondering if you can clarify that for me, please.
Yeah, of course. So actually, Bayesian neural network is a different name for Bayesian UQ, right? So there's different techniques. For example, the most popular ones is concrete dropout. So that's an alternative to variational Bayes, right? So there's also a variational Bayes method, which instead of, it was very similar to our neural process work. It actually minimizes the lower bound of the log likelihood. And then there's also, they're all most of them are approximate Bayesian inference techniques. The exact ones based on stochastic gradient MCMC, right? It's exact ones with basically guarantees that it will guarantee to converge to the posterior, true posterior. It's just very expensive because we have to run multiple Markov chains at the same time. But the nice thing is that because it's embarrassingly parallel, right? So we can run multiple chains in multiple machines simultaneously.
Yeah, great, thank you. Mm-hmm. So we'll check one more time. I don't see any other questions in the chat. If you have one, please put it in now, since we're almost out of time. Let's see, it's a chat. Oh, otherwise, yeah, thank you, Rose, again for joining us and for sharing with us. That was excellent talk.
Of course, thanks for organizing this great workshop. Thank you.
Thank you so much. So, hello, George.
Hi.
Would you like to share your screen to make sure everything works fine?
Yep.